All right, so we can now define the trigonometric functions now that we have this idea of a unit circle and angles on the unit circle and terminal points. So if you haven't seen that video, then make sure that you watch that before you look at this. So what are the trigonometric functions? Apart from having a long name that takes me a while to write on the board, what are they? Well, there's actually 6 different trigonometric functions, and we'll get to why they're called trigonometric functions in a little bit. It turns out that although we're going to think about defining these functions by using the unit circle, it turns out that they actually are very significant for thinking about triangles, and that's why they're called trigonometric functions or trig functions, because they kind of have to do with the geometry of triangles. So the idea behind the trig functions, there are 2 basic trig functions, and the other 4, remember I said there's a total of 6, so the other 4 are defined in terms of these basic functions. The 2 basic functions are the sine function and the cosine function. You can kind of guess by the fact that one is sine, one is cosine. These actually have some nice relationships with one another that we will see as we define them and start looking at their properties. But first we have to look at how do you define these things. In order to write these functions, these are the names of the functions, sine and cosine, but we usually abbreviate them when we write them as functions. So the function sin of theta, this would be the sine of theta. And if I write cos of theta, which I just read as cos theta, that would mean the cosine of theta. But what are these things? Well, think back to the unit circle that we drew last time. Give me a moment to draw a new one. If I have some angle theta, I have a terminal point for this angle theta. Remember, we said that the terminal point is just wherever the radial line at that angle intersects with the unit circle. So this is going to be my terminal point. We define the sine function to be the y coordinate of the terminal point. We define the cosine function to be the x coordinate of the terminal point. And there's a really nice way of remembering this. If we just think about this picture with the unit circle, I can just say that this terminal point has coordinates cosine theta, comma, sine theta. And this is the definition of these functions. These are well-defined functions because for any given angle, you give me any angle you want to, and I can just say, okay, I'm going to traverse the circle until I hit whatever angle that happens to be, and then I just look at, well, where am I now? What is the terminal point? And then I ask, what's the x-coordinate? That gives me cosine. And what is the y-coordinate? That's going to give me sine. And that's really all that we have to do in order to define the trigonometric functions. Now, I said that there are several other trigonometric functions, so I will just very quickly tell you what are the definitions of the other trig functions, but make sure that you write this down first so you can pause this for a moment if you need to take a moment to take some notes. The other 4 functions are defined in terms of the sine and cosine. So we have the tangent, which is written as tan theta, and I would just read that as tan theta. And this is defined to be the sine of theta divided by the cosine of theta. Then we have the cotangent. This is written as COT of theta, which usually I just say cot theta or cotan theta. Sometimes I just say cotangent theta. And this is cosine theta divided by sine theta. Notice that this is actually the reciprocal of the tangent. So tangent and cotangent are very closely related. One is just the reciprocal of the other. Next up, we have the secant. This is written SEC of theta, and this is defined to be the reciprocal of the cosine. Finally, we have the cosecant. This is written as CSC of theta, and it is the reciprocal of the sine function of theta. That's a terrible theta. Let me rewrite that theta a little bit. So, altogether, we have 6 trigonometric functions, but they're all defined in terms of sines and cosines, and the sines and cosines are simply defined in terms of the terminal points of an angle on the unit circle. Now, some nice properties that we can immediately kind of see. I want to show you how this is kind of a weird definition on the one hand, because we don't really have a formula for it. It turns out that there aren't actually nice formulas for sine theta and cosine theta. It turns out that it's actually a little bit difficult to figure out what exactly happens if you want to compute an exact number here. We'll see how we can do that in some cases later on, but in general, there's no nice formula for sine or cosine. But we can still say quite a bit about these functions. So I'm going to erase this. You might want to pause this and take notes if you haven't written this down yet. So the first property that I want to observe is that for any terminal point, we have the relationship x squared plus y squared is equal to 1 squared. Well, 1 squared is really just 1. And if the x-coordinate is the cosine and the y-coordinate is the sine, then this gives us cosine squared theta plus sine squared theta equals 1. Now, I should say something really quickly about this notation, because I wrote this down, and now I'm going to tell you what it means. When we want to square the trig functions, we just put the square next to the function. So, cosine squared theta, this is equal to take the cosine of theta and then square it. Sine squared theta, this means take the sine of theta and then square it. We use these abbreviations because it turns out that there's a lot of situations where we're going to end up squaring trig functions, taking trig functions to powers and whatnot, and having to constantly put these parentheses and put the square outside would just be a lot of extra writing. Remember, mathematicians tend to be lazy. We like to come up with the most efficient notation possible for things. So, try not to get confused by this notation. Once you get used to it, it's really pretty straightforward. But this is one of the observations that we can make about these trigonometric functions. And it just follows from this definition in terms of the unit circle. And really, this is just the Pythagorean theorem. That's all it is. Now, we'll return to the Pythagorean theorem in a little bit when we talk about some properties of the other trig functions, but for now I want to focus in just on sines and cosines. So, let's think of if there's anything else that we can say about sine and cosine. And again, if you guys didn't have your notes down, just rewind a little bit, pause, and take the notes. Okay, so let me make a little unit circle over here that we can refer back to. Here's my angle theta, and here's the terminal point, and it's going to have the coordinates cosine theta, comma, sine theta. Well, here's one thing to notice. If I were to go down to negative theta, remember, the negative angles, they just go backwards. They go clockwise instead of counterclockwise. So the coordinate down here is going to be cosine of theta. It has the same x coordinate, but it's negative of the y coordinate. So we get negative sine of the original theta. So this tells me that the cosine of negative theta is equal to theta. It also tells me that the sine of negative theta is equal to, why did I write theta? No, the cosine of negative theta is equal to the cosine of theta. The sine of negative theta is equal to negative sine of theta. Now, you may not have heard these terms before, but when you have this kind of property, we call such functions even functions. And we call functions with this kind of property, where you can bring the negative outside of the function, we call these odd functions. The reason that we call them that is because if I have an even function, then its graph is going to look something like the graph of a polynomial which only involves even degrees. So if I look at a graph of an even function, then the right-hand half of the graph and the left-hand half of the graph have to be the same if I take a mirror image horizontally. In other words, if I flip the graph over the y-axis, it doesn't actually change the graph. It switches the two sides and mirror images them, but I get exactly the same shape. With odd functions, these look kind of like the graphs of a polynomial whose powers are all odd numbers. And in this case, what's going to happen is that the left-hand side will be the same as the right-hand side, except it will be the negative of it. So if I have the right-hand side of the graph, I can flip it horizontally over the y-axis, and then I flip it vertically over the x-axis, and that will give me the same picture. Now, let's take a look at a couple of other properties here of sine and cosine. The next property that I want to observe, and I don't know why I just erased the unit circle. I actually kind of wanted to have a unit circle that I could refer to. Let's put that unit circle back. And here's my terminal point, cosine theta, comma, sine theta. Okay, the observation that I want to make, and we already sort of said this, is that if I change the angle by a multiple of 2 pi, I get back exactly what I started with, in the sense that I end up back at the same terminal point. So one of the things that this tells me, sorry for that little smudge there, one of the things that this tells me is that the cosine of theta plus any multiple of 2 pi is the same as the cosine of the angle theta. And the same is true for sine. The sine of theta plus any multiple of 2 pi is going to be equal to the sine of theta. You change the angle by a multiple of 2 pi, it does not change the terminal point. If it doesn't change the terminal point, then it doesn't change the x or the y coordinates, which are just the cosine and the sine. This is kind of interesting because it means that every time we go by 2 pi in our variable, these cosine and sine functions just start repeating themselves. In other words, we're going to get the same pattern repeating over and over and over again as we look at our graph, as we think about our function. And this is kind of different. A polynomial can't do this. Polynomials eventually either have to approach, polynomials in particular, they either have to just be a straight line, or eventually they're going to have to diverge up to infinity or down to negative infinity. They cannot keep on repeating. But the cosine and the sine, these do keep on repeating. And this tells us, among other things, there is no polynomial formula for cosine or for sine. These functions, whatever they are, if we could come up with a formula for them, they can't simply be polynomials. Another way of thinking about this is to notice that if I wanted to think about, let's just take cosine as an example. If I wanted to know what are the solutions to cosine of x equals 0, well, x could be equal to 0, because at an angle of 0, why did I say 0? X could be equal to pi over 2, because, well, at pi over 2, the x coordinate is 0. It could also be equal to negative pi over 2, because if I go down this direction to negative pi over 2, that would also have an x coordinate of 0. But then I could also start adding multiples of 2 pi to this. So I could get 2 pi plus pi over 2. I could get 4 pi plus pi over 2. I could do the same thing with the minus pi over 2. There are infinitely many solutions. Well, this is impossible if cosine were a polynomial, because remember, the number of solutions to a polynomial, counting multiplicities, has to be less than or equal to the degree of the polynomial. You can't have an infinite degree polynomial, so because this has an infinite number of zeros, that means this cannot be expressed as a polynomial function. Now, by the way, functions that have this kind of a property, these have a special name, and these are called periodic functions with period 2 pi. What that means is that every time we shift by an interval of width 2 pi, the function repeats itself. More generally, what you can have are periodic functions that have different periods. So in general, a function which is periodic with a period of, let's say, a, this obeys the equation f of x plus a equals f of x. And we take the period to be the smallest a for which this is true. So the period is the smallest a for which this is true. The reason we have to be careful about that is because if this is true, then it would also be true if I added 2 times a or 3 times a, because I could break this up into x plus 2a comes back to f of x plus a, which comes back to f of x. So we want to take the period to be the smallest shift in the variable that we need to make in order to start repeating the same pattern over and over again. Now, that doesn't necessarily mean you can't get the same value sometimes within that interval, but it does mean you don't start repeating the same pattern until you have gone through one full period, meaning the width of this interval before it starts repeating itself again. One thing that we can observe from this is that the tangent function, remember we defined the tangent function in terms of sines and cosines a few minutes ago, well, it turns out that that is also periodic, but it has a slightly different period. So tangent of theta is equal to sine of theta over cosine of theta. Now, I want to make an observation here about sine and cosine, which is going to be very useful for what I want to say about tangent in a moment. Namely, suppose that I have some angle theta here, and this is going to have the coordinates cosine theta, sine theta as usual. Well, what happens if I take theta plus pi? It just gets me straight across. Basically, if I look at this circle, this is a straight line. It is a diameter of this circle. So, what are the coordinates down here going to be? Well, the coordinates down here are going to be, I'm going to flip cosine and I'm going to flip sine as well. So we're going to have negative cosine theta, negative sine theta for this terminal point down here. Sorry, I was in the way there for a moment. So what we can say about this is that the sine of theta plus pi is equal to negative sine theta, and the cosine of theta plus pi is negative cosine theta. What does this tell us about the tangent function? Well, if I take the tangent of theta plus pi, this is going to be equal to the sine of theta plus pi divided by cosine of theta plus pi. But this is just going to be equal to negative sine theta over negative cosine theta. And what happens to these negatives? Well, they're going to cancel with one another and leave me with just sine theta over cosine theta, which is tangent theta. So what we see here is that the tangent of theta has a period of pi. This might be a little surprising because when you first think about it, since tangent is sine over cosine, well, these guys are periodic with period 2 pi. They repeat themselves every 2 pi. So we might expect tangent to be periodic with period 2 pi, and it does repeat itself every 2 pi, but it actually has a smaller period than that. The period is pi itself, not twice pi. And that's just, like I said, it's because we can end up factoring out this, we bring out this negative, the negatives cancel, and that gives us this period. One last thing I want to do here is I want to give a quick sketch of what does the sine function sort of look like and what does the cosine function sort of look like. We're just going to get a sort of very quick idea of this here. And then later, when we start talking about exact values, then we can make this picture a little bit bigger. But keep erasing my unit circles, which is not really ideal for going through this. Here's my unit circle. What is going to happen to the y coordinates here? So we're going to make a theta graph versus the sine of theta here. Let's actually say this axis, we'll call it t, and then we're going to make a graph of t equals sine theta. Well, I can see that at an angle of 0, I would start out with a y coordinate of 0. And by the time I hit pi over 2, I should come up to a height of 1, because at that point the y coordinate is 1. Then I'm going to come back down to 0 at pi. Then at 3 pi over 2, I should be down here at negative 1. And finally, when I hit 2 pi, I should be back where I started with. And it's going to start off, the sine function starts off increasing pretty quickly because at first changing theta mostly moves my point vertically. But as I get closer to pi over 2, it's going to slow down how fast it increases. So we're going to get something that looks like this, and then it's going to do the opposite as I come down. It's going to start decreasing kind of slowly, and then it's going to start going down faster as we come over towards negative 1. And then over here, we get the same thing, but sort of upside down. Now, if you wanted to extend this, you could use the fact that this is periodic. So you could say, well, this graph is just going to keep on repeating itself forever. So over here at minus pi over 2, we would be down here at negative 1. We would come back up to 0 at minus pi, and we would keep on going. We could keep on going to the right as well, except that my whiteboard is kind of too small. We'll come back to this and fill in some more points later on, but this is kind of the general shape that we get from this. Now, what about the cosine of theta? So take notes. I'm about to erase this, so pause it if you need to. Okay, so now what if I wanted to do, once again, we're going to do a theta t graph here, and we're going to graph t equals cosine theta. Well, this time, at an angle of 0, the cosine is equal to 1 because the x-coordinate here is 1, 0. And it's going to start off decreasing kind of slowly until it decreases to 0 at pi over 2. So we get this kind of a shape. Then it continues decreasing until we get to -1 at pi. It keeps on, now it starts increasing. I'm sorry, it doesn't keep decreasing. It changes to increasing as we go from minus pi to 3 pi over 2. And when we hit 2 pi, it comes back up to +1. And of course, we can keep on extending this. So at negative pi over 2, it would come back down here. It hits -1 again at minus pi. I could keep on going in this direction as well. Yeah, again, small whiteboard. Sorry about that. You can look in your book. It has much nicer graphs that are made of these things, and you can look at that. But basically, this shape just keeps on repeating. You'll notice this is kind of a similar shape to what we got for sine theta. It's just been shifted a bit, and that is not really a coincidence. In fact, we will look at a relationship between sine and cosine later on, which is going to explain exactly why these two things look so similar to one another. But that's the basic shape of these graphs. All right, so the next thing that we're going to want to do is we're going to want to explain, 1, how does this all relate to triangles? And 2, how can we actually figure out what sine and cosine are equal to for some various values? We've seen how to do it at an angle of 0, at pi over 2, at pi, and at 3 pi over 2. But we'd like to be able to do something more than that. We'd like to be able to get a little bit more in there. So that's what we're going to pursue next time. However, for here, I'm going to stop this video, and you guys can take a little break and come back to watching the next video when you get around to it.